All right. What is up, everybody? Tom McGurl here with another episode of our Learn Rust live stream. We're going through the Rust book. We're learning together. We are doing chapter 10 this evening. If you haven't been following, we've been going through chapters. We started with chapter 1, 2, 3. We did them all, and now we're on chapter 10. It's going to be a good time. Thank you for stopping by if you're on stream. If you're watching later on YouTube, fantastic. And of course, as usual, if you've missed any episodes, do not worry. We got the YouTube here. You can search Tom McGurl, find the channel. We have all the chapters from part 1 onward. We did some exercises, chapter 8. That'd be part 8 here. Last week we did chapter 9. It was a lot of fun. Again, the streams are every Tuesday, 9 p.m. to 11 p.m. Eastern Time. We're on Eastern Standard Time now. And there's other videos up here for you to check out if you want to see some other videos in the series. We did one on building a serverless API with AWS Lambda. So really cool. We got to dive in with the AWS ecosystem. We built that with Node.js using TypeScript. We backed it with a DynamoDB database and some file storage using S3 for images. So super cool. And then before that, we tried out Recoil.js by building a React Native app using Expo, which scaffolds out your React Native app. We use TypeScript for that, Recoil.js obviously, and React. So really great. That's a big series, 7 parts. The serverless one's only 1 part, so check it out. If you like what you see there, subscribe and you'll get notifications for when new videos get posted. This video, if you're watching it live, will be posted tomorrow. Everything goes up the following evening. And yeah, just check it out. If you want to get updates for when I go live, as always, check the Twitter. My Twitter handle is above. It's going to stay there above my name, so check that out. I post when I go live, other programming things like that. So if you want to follow along with anything we've done, or if you see anything interesting in the videos, you want to check out where the code is, it's posted all on my GitHub here. We have our Brewbook React Native. That's the React Native app we built with Recoil.js. We have Learn Rust Live, which is what we're doing right now. All the chapters, you see chapter 9's posted. They all get posted here, so check them out. Pull down the code or create your own repo. Follow along yourself, whatever you think works for you. We also have other repos here. The serverless API for the AWS Lambda work is all here, so check it out. But today, we're going to be doing the big chapter 10. If you've been watching the stream or following along on YouTube, you will know that chapter 10 has been looming, right? We've been talking about it. It's come up in almost every chapter. We'll see something that says, oh, chapter 10. Chapter 10, this will be covered in chapter 10. So today we are doing the infamous, notorious, famous, whatever you want to call it, chapter 10. I'm excited. I hope you're excited. And we're going to be covering generic types, traits, and something else, I believe, generic types, traits, and lifetime. So hopefully we'll get through the whole thing. If we don't, we'll stop at 11. We'll continue next week with whatever we do not finish, but who knows, maybe we'll finish. If you've been following, we always start by thanking the authors of this fantastic book. So once again, shout out to Steve Klobnik, Carol Nichols, and anyone from the Rust community who's contributed to this book. We couldn't be here doing this without those contributions and without that authorship. So really appreciate this. It's a fantastic book. I've learned a ton. I hope you've learned a ton if you've been following along. And it's just been really fun. So I'm going to continue with it. We've already 9 chapters in, which may not sound like a lot, but we've gotten a lot done. And again, check that YouTube and watch some of the streams. You can watch them at 1.7 speed, 2 times speed. You can watch them in slow-mo. Show us your secrets, Russ. So yeah, we'll show you my GitHub secrets. So yeah, everything is here. But today, it's all about chapter 10. Come on. We've been waiting for this moment. We've been talking about generic types at a very shallow level. We've been using traits behind the scenes, right? Lifetimes we haven't gotten too much into, except when we were talking about borrowing. We're going to dive into that now. So without further ado, let's get started. Again, as always, if you have any questions, any comments, pop them in the chat. If you like what you see and you haven't already, follow the stream and you can get notified when I go live Tuesdays, 9 p.m. to 11 p.m. We might be adding another day in the future. We did Wednesday last week because of the U.S. elections, and we may do Wednesdays going forward. We'll see. Maybe some more one-off stuff. One of the things I do want to try that I wanted to mention, I'm going to pull it up here. Russ Lang is the Rustlings repo. So it's this awesome repo. I had heard about it on a podcast and saw here on the Rust community website. But it is a really fun interactive CLI tutorial where you solve some exercises by making tests pass with Rust programs. So I think we're going to go through that at some point because that is really fun. I did the first few exercises and I think it'd be something that you all would enjoy seeing on stream. But let's jump in. Chapter 10, right? What is chapter 10? Generic types, traits, and lifetimes. Lifetimes, all right? Every programming language has tools for effectively handling and the decoupling of concepts. In Rust, one such tool is generics. Generics are abstract stand-ins for concrete types or other properties. When we're writing code, we can express the behavior of a generic or how they relate to other generics without knowing what will be in their place when compiling and running code. What does this mean? We're going to deal with functions that can handle types that have a certain behavior. And you may not know if it's going to be a string at the runtime. You may not know if a integer is going to be passed, but whatever you do in there, you're ensuring that the type you're operating on can handle that operation. And the compiler is going to help us with that. But our generic types and how we define them are also going to help. And we'll see that pretty soon. Similar way function takes parameters with unknown values to run the same code on multiple concrete values. Functions can take parameters of some generic type instead of concrete type, like an integer 32 or a string. In fact, we've already used generics in chapter 6 with the option t, chapter 8 with the vector and the hash map, and chapter 9, just what we did last week, where we used the result te, which was a result of a certain type or an option, right? In this chapter, we're going to explore how to define your own types, functions, and methods with generics. Pretty exciting stuff. First, we'll review how to extract a function to reduce code duplication. Next, we'll use the same technique to make a generic function from two functions that differ only in the types of their parameters. We'll also explain how to use generic types in struct and enum definitions. We've learned about struct, we learned about enums. Now we're going to see how to implement generic types along with those. Then we'll learn how to use traits and define behavior in a generic way. You can combine traits with generic types to constrain a generic type to only those types that have particular behavior as opposed to just any type, right? So maybe it's types that allow you to get a length or types that allow you to consume them with a generator or with, using .next with an iterator, I should say. Finally, we'll discuss lifetimes, a variety of generics that give compiler information about how references relate to each other. Lifetimes allow us to borrow values in many situations while still enabling the compiler to check that the references are valid. All right. So first, we're going to start out with removing duplication by extracting a function. So what I'm going to do is I'm going to pop this over here as I usually do. And we are going to open up our code here where we're following along. I'm just going to close some stuff here. Discord. And let's just go ahead and create, if we don't have one already, a folder for this. So we have chapter 9. I'm going to create a new folder. Chapter 10. Oh, I don't want to create it there. Create a new folder here. Chapter 10. That's a file. Chapter 10. We'll call it generics, traits, lifetimes. All right, so first what I'm going to do is I'm going to go ahead and create a folder here where we can start trying out generic types. So I'm going to use cargo for that. So I'll go into chapter 10 here. Projects, chapter 10, and I'll do cargo new generic types. Go into generic types. All right, awesome. And so that's going to create this folder here. If you've seen us, if you've been following along, you know that we use cargo to create new projects. So we have our main function here, and I'm just going to kind of mess around with what we have here. So I'm going to copy this code. So this code, what it's going to do is find the length of a vector. So I'll copy it here, paste it here. So what does it do? Let's walk through it. We get a set of integers that we create a vector. You've seen the vector macro. That's right there. That's instead of us saying, vector new. We're going to create a mutable variable called largest, where we're going to store the largest variable. We're going to start that, the largest integer. We're going to start that at the first index. So it's going to start out as 34. Then we're going to traverse that list using a classic for loop. And if the number at the current position is larger than our current largest number, we'll reset the largest number to that number. Then print that number, and here is a test. So we haven't seen how to write tests yet, but we've seen them a few times, and it seemed pretty clear. We just use these assertions. So it's saying assert the largest is 100. So what I'm going to do is I'm going to run this code. And there you go. Hello, it prints out. Oh, I'm in the wrong project. Hold on. Generic types. Largest number is, let's see. Did I put this in the wrong place? Generic types. Oh, I gotta save it. Duh. Cargo run, and there you go. Largest number is 100. So awesome. Our test passed, and we're all good. Now, we can see that this code stores, we just walked through it here, and it's going to find that the largest is 100. But now, what if we want to find the largest number in two lists of numbers? We can duplicate the code. So this is a classic example of code duplication. And if you've been programming before, you know that when you see duplicate code like this, we try to move it out to a function. But so what I'm going to do is just copy this extra bit here, where we have a second vector defined. And so here, the second vector, the largest number should be 6,000. So I'm going to copy this assertion, paste it down here, and change this to 6,000. And so you'll notice what we did here is we created number list. And it's okay that we reuse this. Again, remember we can shadow values, right? We can change them. So we shadowed number list, changed it to this vector. And then we shadowed largest here by creating a new largest. And we did exactly the same thing. And if I just run this, we're going to get the same results, right? So we're going to get 6,100. So perfect, that all works. But we've duplicated code, right? And so it says here, although the code works, duplicating code is tedious and error prone. We also have to update the code in multiple places when we want to change it. So if I wanted to change how I'm calculating largest, I'd have to do it in 2 places. And that's a little much to keep track of. And it's also adds to the length of our code and the complexity ultimately. So in this next listing, we've extracted the code that finds the largest number into a function named largest. Unlike the code above it, which can find the largest number in only one particular list, this program can find the largest number in 2 different lists. So we're going to extract that code. So let's put that up here. I'm just going to write it out so I can get some experience typing it. So we're going to take a list, and what is the type of that list? Well, it's going to be a vector. It's going to be a reference to a vector of signed 32-bit integers. And what is it going to return? It's going to return a reference to a vector, or it's going to return a reference to a signed 32-bit integer, which would be the largest number. What it is, boys, does, welcome to the chat. What's your vector, Victor? Hello. Thanks for stopping by. All right, so we're going to create our mutable largest number, and I'm just going to copy this code here, and we'll just change it a bit. So we got largest, that's great. And instead of number list, it's just going to be list. List. Here we're going to say list. And so what we're doing here is we're saying let mute largest. And you'll notice that we have a reference to a list. So what I'm going to want to do is go ahead and grab that reference because that's what we're going to be returning. And at the end, I want to return largest. And again, I'm leaving out the semicolon because it has implicit returns. And so now we have this largest file. And now what we can do is we can call it, like you can see down here, we can simply call that here. So what we'll do is we'll say mute largest equals, and we'll just set it to, and in their case, they're using result. So we'll do the same thing. So we'll say let result equal largest. And what are we going to pass it? We're going to pass it our vector. In this case, it's called number list, but we're not going to pass it number list directly. We're going to pass it a reference so that it doesn't take ownership. And then we're going to print out result here. And then we're going to assert that result is 100. And we're going to do the same thing here, but with the new list. So we're going to shadow result equal largest, pass it that reference to number list, which again, we still have access to because we passed a reference. And we're going to print out result. All right, so now let's go ahead and run that code. So I'm just gonna go here and run that. All right, I have an issue. No invitation for, because I have a reference to integer 32 and I can't compare that to an integer directly. So all I have to do there, and we can see it down here, is largest, I'm passing a number list. I can't assert result. What I can do is I can grab the value there, right? So I can say, and that's going to grab the value at result. So adding that asterisk there to get the value at that reference, and there we go. Now it all works. So now we're correctly using references and dereferencing it, and you can see it worked. And if you've done programming, again, if you've done programming before, and you've probably come across this pattern where you have duplicated code, you want to break it out into its own function, and so you do so. And here you can see we did it a little bit differently because we broke the function out of our main scope. We needed to use referencing so that that largest function wouldn't take ownership. It wasn't an issue before because, again, we were within the same scope. So largest function has a parameter called list, which represents any concrete slice of integer 32's values that might pass into that function. As a result, when we call the function, the code runs on the specific values that we pass in. In sum, here are some steps. We want to change the code from listing 10.2 to 10.3. So we identify there's duplicate code. We extract the duplicate code into the body of a function and specify the inputs and return values of that code in the function signature, which we did here. And update the two instances of duplicated code to call the function instead, and we did that. So next, we're going to use the same steps with generics to reduce code duplication in different ways. In the same way that the function body can operate on an abstract list instead of specific values, generics allow code to operate on abstract types. So here it operated on any list. It didn't care what the list was. Now we're going to see how to make it not even care what the values are. For example, say we had two functions, one that finds the largest slice in a vector of signed 32-bit integer values, and one that finds the largest item in a slice of character values. How would we eliminate that duplication? Let's find out, right? Let's find it out. So let's see, generic types. We can use generics to create definitions for items like function signatures or structs, which we can then use with many different concrete data types. Let's first look at how to define functions, structs, enums, and methods using generics. Then we'll discuss how to generate effect and how generics affect code performance. So we're going to see how they actually affect the performance of our code. So in function definitions, when defining a function that uses generics, we place the generics in the signature of the function, where we would usually specify the data types of the parameters and return values. So what we're talking about right here, this is the function's signature in this example. So doing this makes our code more flexible and provides more functionality to callers of our function while preventing code duplication. So it allows it to be more flexible, prevents code duplication, and we're going to see in a second, it still allows us to be type safe. Continuing with our largest function, in listing 10.4, it shows two functions that both find the largest value in a slice. So we have largest I32, which is what we have here. So I'll change that to I32. All right. And then I'm going to add this largest character, which will do the same thing but for a character list. So let's copy this here. There we go. So we have largest car, and that works on a character list. And I'm just going to go ahead and change this list here to car list, and we'll do what they have here. We're going to change it up a little bit. So we're going to do you know where I'm going with this? Come on. Switch, and we're going to call largest car here. We're going to pass it the car list. Whoa, what's going on? Car list. And then here what we're going to do is we're going to assert, we're going to say the largest car, and again, largest car, it's just talking about alphabetical, right? Don't be like, oh, which one's like physically larger? No, just going to be which one is the largest in terms of alphabetical order. So the largest car is, and we're going to pass it result. And so we're going to assert that result is W. So I'm going to go ahead and run this code. Cool. Largest number is 100. Largest character is W. Awesome. That works. Now, let's see how we can combine these two functions, right? That's the whole point of generics. So let's look at that. So to parameterize these types in the new functions we'll define, we'll need to name the type parameter just as we do for the value parameters to a function, right? So, but we can use any identifier as a type parameter, name, but we'll use T because that's the convention. Parameter names in Rust are short, often just one letter, and in Rust, type naming convention is camel case, short for type, capital T, is the default choice for most Rust programmers. And if you use other languages, probably like Java, even TypeScript, you've probably seen this generic capital T being used as a pattern. When we use a parameter in the body of the function, we'll have to declare the parameter name in the signature so the compiler knows what the name means. Similarly, when we use a type parameter name in a function signature, we'll have to declare the type parameter name before we use it. To define the generic largest function, place type name declarations inside angle brackets between the name of the function and the parameter like this. So you can see the new function name. So I'm just going to create that below here, largest. And so we need to include it in the function name. That's important. And it looks different already, right? Here we have the arguments right after the function name. Now we're going to have the generic T there. And then we're going to say our list is a reference of a vector containing T. And it's going to return a reference to a type, right? So it's generic. We got the brackets, type T, the big T. It's going to operate on a list of said type, and it's going to return a reference of said type. And so we read this definition as the function largest is generic over some type T, right? So largest is generic over some type T. This function has one parameter named list, which we see here, right? That's the only parameter, list, which is a slice of values of type T. The largest function will return a reference to a value of the same type, T. So it's, again, we read this part here as the largest function is generic over some type T. It has a parameter list, which is a value of slices of type T, and it returns a reference to a value of type T. So it's very wordy, but all you're worried about here is this T is referring to the type of the thing that we're dealing with, right? Okay, so here it shows the combined largest function definition using the generic data types in its signature. It also shows how we can call the function with either a slice of signed 32-bit integer values or character values. It says, note this code won't compile yet, but we'll fix it later in this chapter. So I'm going to create largest T here. So we're going to create our mutable largest value. It's just going to be list 0, and it's basically the same code. So I can pretty much copy this code here. Because again, the code's not going to change much. The one thing that is going to change, which you'll notice, is we're going to get rid of that reference here. Well, actually, we're going to keep it there. Okay, so it says not going to compile, so we're not going to switch to using it yet. We're going to see what we're doing in a second. But let me just remove this. And it's going to tell you it's not going to be able to compile. And that's okay. For now, we're going to wait to compile this anyway. So if we compile it right now, we'll get this error. T might need a bound for standard CMP partial OR. So let me show that here. Let me just change this and it should show it. Let's try to compile it. We'll see it. So let me clear this. And remember, to compile alone, we just run cargo check. And here you go. So we can see here, binary operator cannot be applied to type reference of T. T, consider restricting type parameter T. And it says here, standard compare partial ORed. So we need to implement that. We'll see what that is in a second. So here it says, The note mentions standard compare partial order, which is a trait. We'll talk about traits in the next section. For now, the error states that the body of largest won't work for all possible types that T could be, because we want to compare values of type T in the body, right? That's what we're comparing. And so it needs to make sure that whatever we pass has that ability, essentially, or that trait. We can only use types whose value can be ordered, right? That we can actually compare. Largest characters, you can figure out characters, alphabetical order, numbers, it's easy to compare largest. But how do you compare largest when you're looking at structures or tuples, right? To enable comparisons, the standard library has the standard compare partial order trait that we can implement on types. See Appendix C for more on this trait. You'll learn how to specify that a generic type has a particular trait in the traits as parameters section, but let's first explore other ways of using generic type parameters. Okay, cool. So other ways of using generic type parameters. So what I'm going to do is just comment this out here, and I'm going to create a struct called point, like they're doing here. So we'll do struct, just move this out of the way here. All right, so we're going to create a struct point that's generic on type T, and we have X of type T and Y of type T, generic type. And then down here, we're just going to add, right here, I'm just going to add let integer equal point X5, Y10, and let float equal X 1.0, and we're going to put float values here, and here 4.0. And so you can see it's not complaining, it's complaining that they're not used, but it's not complaining that we created an invalid point, because we've created a point that is generic on type T. So passing it a float and passing it a signed, or in this case, unsigned 32-bit integer is absolutely acceptable. So here we can see, note, because we've only used one generic type to define point T, this definition says that the point T struct is generic over some type T, and the fields X and Y are both the same type, whatever the type may be. If we create an instance of point T that has values of different types, it'll complain. So if we were to say 4 here, it's going to complain, and if we hover, it's going to tell us here, let me pull this up here, I changed this to 4, it says expected floating point number. So it's expecting us, the T's, to be the same type, right? Not two different types. So that's an important feature. Okay, so in this example, when we assign the integer value 5 to X, or in our case, we assigned Y to 4, we let the compiler know that the generic type T will be an integer for this instance. So here we're saying it's going to be an integer, here we're saying it's going to be a float, and then we get that type mismatch. So pretty cool. So to define a type where they can both be different generics, we can use a different letter. And so here it says we can change the definition of point to be generic over types T and U, where X is of type T and Y is of type U. What does that look like? Well, I just change it here to U and save that, and we see, what does this say? Cannot find type U in this scope. A type parameter with a similar scope T exists. So we can change this here. So it says now all instances of point shown are allowed. But let's see, why is it complaining about this? Oh, because I need to say here it's point type T, so it's parameterized over T and U, and now I can use those successfully. So pretty cool. So we can be pretty flexible with how we define these structures and how we define many different generic types. The enum definitions. As we do with structs, we can define enums that hold generic data types and their variants. Let's take another look at option T enum from the standard library, which we've seen before, right? It either has some value of type T, that's the generic, or none. So the definition should now make more sense to you. As you can see, option T is an enum that is generic over type T and has two variants, some, which holds the value of type T, and none variant, which doesn't hold any value. By using option T enum, we can express the abstract concept of having an optional value. And because option T is generic, we can use this abstraction no matter what the type of value that is optional is. So that's really cool, right? So we can have a option of any type, right? We can have an option of a struct, we can have an option of a boolean, an option of an integer. It lets us express that. So it's really, really nice. We've also seen it with result in the last chapter. So this is the type definition for result. So you have OK, where it has the value t, and it has the error variant, right? So here it says, the result enum is generic over two types, t and e. It has two variants, OK, which holds the value of type t, and error, which holds the value of type e. The definition makes it convenient to use the result enum anywhere we have an operation that might succeed, return a value of a type t, or fail and return an error of some type e. In fact, it's what we used to open a file in chapter 9, right? Where t was filled with the type standard file system file when we had a successful open of that file, and it was e when it was filled with the standard IO error when there was an issue opening it, whether it couldn't find the file or whatnot. When you recognize situations in your code with multiple struct or enum definitions that differ only in the types of the values they hold, you can avoid duplication by using generic types instead. So that's pretty awesome. It's definitely going to be very useful, especially as you make functions that you want to be able to operate over different types, right? Which we've already seen with largest, but maybe like more practical examples, right? Option and result are practical examples. We can use results with opening a file. We could use results when we're trying to make maybe a web request, right? An HTTP request. We haven't seen that yet, but I'm assuming that could be useful. We can use generics in method definitions. We can implement methods or structs and enums, we did in chapter 5, and use generic types in their definitions. Listing 10.9 shows point t struct we defined from the previous listing with the named method x implemented on it. So we have our point t, and we can implement here. We can do, remember this is the implementation block, and we can say t, point t, change this back to t here. I'm gonna make this one here. And so here we have implementation block for point t, and we have a function called x that gets self. We learned that when we learned about implementation blocks, and it's going to return a reference to a type t, and it's going to return self.x. And so this is useful because sometimes we want to make properties of a structure private, and this gives a public accessor to those properties. So this is a nice way to give access to x explicitly, right? So pretty cool. And then here, let's do this. Let's do what they've done here. Let's change these back to x1. Let me scroll down so you can see. I'm going to change this back to a float. And what I'm going to do here is I'm going to create another point p, or we'll just use our integer point, and we'll do print ln p dot integer dot x equals, and we'll pass it integer dot x. And again, we're calling the function explicitly here. So let's take a look and see what that looks like. And float, it's just saying that it's unused. So what I'll do is I'll just make it, preface it with an underscore, and we won't get that complaint there. And so here I'm just going to go ahead and run that run the code. And there we go, integer point dot x. So the property x of integer is 5. So pretty cool. We used the generic accessor there. Awesome. All right, let's see. We defined a method named x on point t that returns a reference to the data in the field x. Note that we have to declare t just after the implementation. So kind of similar to what we did here, where we declared, where is it? In our largest function here, where we declared t right after the function name. We're doing something very similar here. We're declaring it right after our implementation keyword there. So that's a good thing to note. Rust can identify that the type in the angle brackets in the point is a generic type rather than a concrete type. So it says here we could use, for example, methods that only point to point f32 instances rather than point t. So we could say, you know, this has to be of a type 32-bit integer, and so forth. And so here's another example of where they've created an implementation block that is of type F32. So let's try that out. Then we can get rid of this. We can say it's going to be a 32-bit float. We'll call it distance from origin, as they have. It's going to return a 32-bit float. And our computation is going to be self.x.powy, I'm assuming it's put to the power, plus self, and I'm spelling self wrong, self.y.powy 2 dot square root. And so here it's going to complain because, let's see, why is it complaining? Expected float 32, expected reference to a float 32 and found a float 32. And that's probably because I haven't implemented this. Let's see. Consider borrowing here. So getting a reference. Oh, it's because I'm returning a reference when I don't need to. There we go. So now this is going to return. You can see there in the definition when I hover, this is going to return a 32-bit float. So pretty cool. Let's see if I hover there. Pretty cool. And square root, same thing. Awesome. I love the IntelliSense that we're getting there. All right. This code means the type point float 32-bit integer, or 32-bit float, will have a method named distance from origin, and other instances of point t where t is not of type 32-bit float will not have this method defined. This method measures how far our point is from the point coordinates 0, 0, and uses mathematical operations that are available only to floating point types. So it's saying this operates only on floating point types, right? So that's pretty cool. Generic type parameters in a struct definition aren't always the same as those you use in that struct's method signatures. For example, in the listing below, defines a method mix up. So defines a method mix up on the point t, comma u, so the more complex point, struct from listing 10.8. That method takes another point as a parameter, which might have different types from the self point we're calling mix up on. The method creates a new point instance with the x value from the self point of type t and the y value from the passed in point of type w. So let's look at the code. So that was kind of a mouthful. Let's see what we're talking about here. So here we have our point, our more complex point. We've called it complex point. We have this new implementation block. So I'm going to go ahead and write this right here. And it's parameterized over t and u. And we're adding it to the complex point, right? This is an implementation block for the complex point. And we have a function called mixup. And here it's VW, which is different than VU. And that's what we're going to see in a second. And the function takes self, just like all of the functions do. And we're going to do other. And one thing to note is it's not taking a reference to self. I'm sure there's a reason for that. And other is a point of a different type, V, comma, W, Volkswagen. And it's going to return a point of type T, comma, W. So what is happening here? So mix up our complex point is parameterized over T and U, right? So that's this point. Mix up is going to take a point of type VW. That's why this is here. So we have our point of type VW. And it's going to return a point of type TW. So it's going to take the T from the complex point that is passed, that we're operating on. So in this case, whatever complex point we're operating on, it's going to use that T, and then the W from the point that's passed in. And so we're going to return that here. So we're going to turn a new point, X, which is going to be self.x, and Y, which is going to be other.y. And this is saying expected type parameter T, found parameter type V. VW, TW, VW. Let's see. Other.y. A type parameter was expected, but a different type was found. So expected a type parameter of type T, but it found Y. So what is X in this case? X is of type T. Y should be of type U, or in this case, we want W. So let's see, what do we do here? Wrong number of arguments, expected 1, found 2. So let's see, did I just mess this up? What does this say here? Wrong number of arguments. Interesting. Let me see if I just mistyped it. I'm going to copy this, or it might be that we're just defining it differently. Oh, you know what it is? It's because we didn't use complex point. I messed up. We're dealing with complex points, not points. That's why it expected type T. So it actually did tell me the appropriate information, which is super cool. Complex point. And there we go. Now we have no issues except for this, which is saying wrong number of arguments, expected 1, found 2. Y, TU, implement TU, TU. This needs to be complex points. And we should be good. Awesome. So what's happening again, just to walk through it. In main, we defined a point that has, or in our case, a complex point that has a 32-bit integer for X. Oh, that's down here. Let's implement that here. So we're going to implement this part. I'm just going to throw it down here. P1. Let's copy this. I have to type it all. Awesome. And we'll go ahead and print that down here. And we got to make these complex points. Okay, so let's see what we've done here. So we defined a complex point that has a signed 32-bit integer for X with the value 5 and a 64-bit float for Y with the value of 10.4. The P2 variable is a complex point struct that has a string slice for X with the value of hello and a character for Y with the value of C. So this one here is our VW. So it's different than T and U. So it's just saying it's different, right? And that's why we're able to use a character and a string slice. So P2, slice for X, character for Y. Calling mixup on P1 with the argument P2 gives us P3, which in this case would be, it would have the T from the first point, right? So we'd have 5. And we'd have the W from the second point, which would be C. And so here you can see it'll have the 32-bit integer for X, because X came from P1. It was the T. The P3 variable will have a character for Y, because Y came from P2. That was our W. And the print lm macro will print out X equals 5, Py equals C. So let's try that out. Let's verify that. And there we go, 5C. So again, if we comment this a bit, just to add more clarity, because it can get confusing, let's put here X is the T, Y is the U, and then here we have X is the V, Y is the W, and then here we have X is the V, Y, or sorry, X is the T again, Y is the W. So we've taken T and W, and you can see here that that's what this returns up here. Our complex point returns a complex point of type TW. So pretty cool, pretty cool. The purpose of this example is to demonstrate a situation in which some generic parameter is declared with the implementation block and some are declared with the method definition. Here, the generic parameter T and U are declared after implementation because they go with the struct definition. The generic parameters V and W are declared with the function mixup because they're only relevant to the method. And so that's just talking about here how we've done this here. This is talking about this, and this is talking about the method, right? Pretty cool, complicated, but cool. Makes sense. If you've ever dealt with generics, it can be confusing to find scenarios where they're useful, but I think we've seen one with operating on different lists, or maybe you if you've ever worked with JavaScript, there's some functions that should take something that returns a promise, right? There's a lot of functions that you call that return promises, async functions. So maybe you have things that can operate on a generic type, but always return a promise or something like that. So super useful. And I'm sure as you start to write more code and as we start to write more Rust programs, we're going to see more use cases. Performance of code using generics. You might be wondering whether there's a runtime cost when you're using the generic type parameters. The good news is that Rust implements generics in such a way that your code doesn't run any slower using generic types than it would with concrete types. That's pretty cool. Rust accomplishes this by performing monomorphization. Yo, word of the day. Monomorphization of the code that is using generics at compile time. Monomorphization is the process of turning generic code into specific code by filling in the concrete types that are used when it's compiled. Monomorphization, everybody. Wow. Very cool. In this process, the compiler does the opposite of the steps we use to create the generic function in listing 10.5. The compiler looks at the places where generic code is called and generates code for the concrete types the generic code is called with. Super cool. Let's look at how this works with an example that uses the standard library's option enum. So here we have an integer of sum5 and a float of sum5.0, which is a float, obviously. When Rust compiles this code, it performs monomorphization. During that process, the compiler reads the values that have been used in option T instances and identifies two kinds of option T. One is the 32-bit integer, the other is the 64-bit float. As such, it expands the generic definition of option T into option I32 and option float 64, thereby replacing the generic definition with specific ones. The monomorphized version of the code looks like the following. The generic option T is replaced with the specific definitions. So that's very cool. So it changes this definition to represent this, and now we can handle those concrete types, and so that we don't get that performance impact. Because Rust compiles generic code into code that specifies the type of the instance, we pay no runtime cost for using generics. That's amazing. When the code runs, it performs just as it would if we had duplicated each definition by hand. The process of monomorphization makes Rust generics extremely efficient at runtime. Wow, let's give a shout out. Let's give a shout out in the chat for monomorphization. Wow, that's great. Very cool. All right. That was generics. A lot. If you have never worked with generics, it seems like a lot. I'm sure as we start to write code, we'll find use cases of it. And I like that they approached it by having us write a function, then abstract it, to see where it's useful. And I'm sure we're going to find out more about that. So let's look at traits, and then eventually we'll be able to get this piece of code to compile once we learn about these traits. So what is a trait? A trait tells the Rust compiler about functionality a particular type has and can share with other types. So let's think about this. If we have other languages, think about like compare it to something we're maybe familiar with if you've done programming before. So JavaScript, if you have an object has certain functions, right? Arrays have certain functions, right? You can call map on them for each. An object you can access, right, with dot notation. If you have an array, you can iterate over it, right? So it has different behaviors. You can get the length of it. You can't get the length of an object. If you have a number, right, you can perform some math on it that you couldn't do with not having an integer. In Python, we have lists. You can iterate over lists. You can form list comprehensions. Can't do that on some other types. So we need to make sure when we create a generic function that the types that we're passing, if we're performing operations, that each of the possible types we'll pass to it can in fact perform those operations. And in Rust, we're calling those traits. That they have a trait because they share functionality and they have shared behavior in an abstract way, right? So we can use trait bounds to specify that a generics can be any type that has a behavior. So we can say, hey, we only want generic types that can get a length, and that's what we're going to use for largest. Or hey, we only want generic types that can be added together. So like if you're adding characters or you're adding integers, right? Or integers and floats. Defining a trait. A type's behavior consists of the methods we can call on that type. Different types share the same behavior if we can call the same methods on those types. For example, length, right? If you can call length on something. Trait definitions are a way to group method signatures together to define a set of behaviors necessary to accomplish some purpose. For example, let's say we have multiple structs that hold various kinds and amounts of text. A news article, for example. Structs that hold a news story filed in a particular location and a tweet. So a news article struct holds a news story filed in a particular location and a tweet. That can have at most 280 characters along with metadata that indicates whether it was a new tweet, a retweet, or a reply to a tweet. We want to make a media aggregator library that can display summaries of data that might be stored in a news article or tweet instance. To do this, we need a summary from each type, and we need to request that request that summary by calling summarize method. So whatever struct we're dealing with, we need to get the summary by calling a summarize method on that instance. So below, we're going to see the definition of a summary trait that expresses that behavior. I'm excited. All right, so what I'm going to do first is I just want to have a place to put this stuff. So I'm going to create a new folder here. Now we got traits. All right, awesome. And I'm just going to open up traits, chapter 10. Traits, there's our main. All right, so let's create this public trait. Summary, summarize function. All right, what's this all about? Let's see. Here we declare a trait using the trait keyword and then the trait's name. So that's the public, we have public, the trait keyword is here. This is the trait's name, right? Which is summary in this case. Inside the curly brackets, we declare the method signatures that describe the behaviors of the types that implement this trait, which in this case is a function called summarize that given its instance, can return a string. After the method signature, instead of providing an implementation with curly brackets, we use a semicolon. Okay. All right. Each type implementing this trait must provide its own custom behavior for the body. Oh, so there we go. Yeah, so I have a semicolon there, just making sure. Each type implementing this trait must provide its own custom behavior for the body of the method. So it doesn't matter how they implement it as long as it follows this signature, right? So here we have our semicolon, we have our signature definition. So in the body of their method, they need to be able to handle this. The compiler will enforce that any type that has the summary trait will have the method summarize defined with this signature exactly. So it has to have a function with this signature defined on it. So that's important. So it's almost like if you've, I mean, this is a bad way to put it because it's very different than this, but if a good way to understand it is back when if you ever wrote Java or you've done Python or even JavaScript, newer JavaScript, and you wrote classes and you defined a class called, character, and the character, it's a character for a video game and they have a jump. All characters should be able to jump and slide, right? Then you can create a new character that extends that has that jump and slide functionality. So in this case, we're saying if something has the summary trait, they have to have a function implemented called summarize that returns a string. So pretty cool. A trait can have multiple methods in its body. The method signatures are listed one per line, and each line ends in a semicolon. So we may require that summary has a bunch of different functions. So let's see that. Implementing a trait on a type. Now that we define the desired behavior using the summary trait, we can implement it on the types in our media aggregator. The listing below shows the implementation of the summary trait on the news article struct that uses the headline, the author, and the location to create the return value of summarize. For the tweet struct, we define summarize as the username followed by the entire text of the tweet, assuming the tweet content is already limited to 280 characters. So we can copy this here. So we're going to just copy our I'll just write it out just so I can get some experience writing it. So we create a new struct called news article. We have a headline, that's a string. We have a location, that's a string. And notice that we're making these public. Remember in our previous point example, we didn't make it public, it was private, but we exposed it via an implementation block that exposed the property. Here we're exclusively making all of these properties public. Author and content. Very cool. All right, so now let's create the implementation block for this. We're gonna implement summary for news article. There's that summarize function, and check out the signature. It's gonna look very familiar because it's gonna have to, because it has to match what we've defined in our trait. So we're gonna have that return type be a string. And we're gonna call format, which we're gonna, again, format's gonna create a string of this format. It's like print line. It's like the print line macro, but it's not gonna print it to the console. It's just gonna format the string. But it's the same API essentially. All right, and we're gonna pass it self.headline, self.author, and self.location. All right. And again, implicit return, we're gonna leave off that semicolon so that it returns this string. And format, of course, is gonna have a return type of string. So if I hover over this, I guess it won't show me the macro, but it's gonna have the return type string. Otherwise it would complain. Okay, now let's create that tweet. So again, it's gonna be a different struct, but we want it to have the same trait, summarize. We should be able to summarize both of these. So we're gonna have a username, which is gonna be a string. We're gonna have content, which is gonna be a string. So similar to the other one, but we have some other fields too, right? We're gonna have reply, which is a Boolean on whether or not it's a reply, and retweet, which is a Boolean representing whether or not this is a retweet. We're gonna implement summarize here. I'm just gonna copy this code here, paste it down here, and instead of for news article this time, it's gonna be for tweet. And instead of headline, author, and content, we're gonna format it a bit differently. We're gonna do just username and the content, because it's a summary. We don't want to print the whole thing. It's just a summary. So we're gonna just print out the summarizing information. All right. So implementing a trait on a type is similar to implementing regular methods. The difference is that after the implementation keyword, we put the trait name that we want to implement. Then we use the for keyword and then specify the name of the type we want to implement the trait for. With the implementation block, we put the method signature that the trait definition has defined. Instead of adding a semicolon after each signature, we use the curly braces and we actually put the implementation. So we fill the method body with the specific behavior that we want the methods of the trait to have for the particular type. After implementing the trait, we can call the methods of instances of news article and tweet in the same way we call regular methods like this. Let's do it. This is awesome. So this is really cool. I love this. So what we're gonna do is we're gonna create a tweet. Let me move this down a bit. Let me move over here so I'm out of the way. So we're gonna create a tweet here. And again, this is how we define a struct. We're gonna have a username, string from, I'm making my own tweet, content, thanks for joining the stream. And we're gonna do reply, it's not a reply, and it's not a retweet. So make that false. And so now we have a nice tweet. I probably spelled retweet wrong. Retweet. All right, so we have tweet there, and then we're gonna go ahead and print, we're gonna call summarize to print it. And tweet.summarize. Awesome, let's run it. There you go. One new tweet. Tom McGurl, thanks for joining the stream. Thanks for joining the stream. That's pretty cool. Let's do the same thing for the article. Why not? Let's create a new... I'm going to just copy this code, but I'm going to change it so that it's for an article. Article. What do we call it? News article? News article. It doesn't have a username. It's got an author. Content. Thanks for joining the stream. We finally made it to chapter 10. Doesn't ever reply, doesn't ever retweet, but it does need to have a location and a headline. So let's add a location. We're just gonna say twitch.tv, and then the headline, string, sweet thank you. There we go, just gotta fix headline there. Awesome, and now what I'm gonna do is say one new news article, and we're gonna do, so here we use shadowing, that's why I didn't complain, but I'm just gonna change this to article. There we go, and let's just go ahead and run our code here. And there you go, one new article. Thank you by Tom McGurl, twitch.tv. Because again, our summarize tweets out the headline, the author, and the location, not the actual content. So really cool. This is awesome. So note that because we define the summary trait and the news article and tweet types, so we defined the summary trait, we defined the news article, we defined the tweet types in the same librs. Well, in our case, we didn't do it in librs, we did it in main.rs, but that's not an issue. Again, this is not a library binary, right? This is the main binary, so the root binary. They're all in the same scope. Let's say that the librs is for a crate we've called aggregator, and someone else wants to use our crate's functionality to implement the summary trait on a struct defined within the library's scope. They would need to bring the trait into their scope first. They would do so by specifying use aggregator : summary, which then would enable them to implement summary for their type. So I bet we're going to do that in a second for our larger function, right? I'm excited for that. The summary trait would also need to be a public trait for another crate to implement it. It can't be private, which is why we put the pub in front of it. That's a good note. So one restriction to note with trait implementation is that we can implement a trait on a type only if either the trait or the type is local to our crate. For example, we can implement standard library traits like display on a custom type like tweet. So if you remember display gets called when we pass it this info, right? So this is going to call display. This is going to call debug. This is going to call display. I think it might be the opposite, but that's what, when it supports that, right? Actually, I think this is debug because remember we put derived debug, and this is the display per trait. So display is this, and when we use this, it's saying that whatever this is, in our case, it's a string. So if I hover over this, you'll see that this returns a string. String implements the display trait, and that's why we're able to use this on it. So pretty cool. So we implement the standard library trait like display on a custom type like tweet as part of our aggregator crate functionality because the type tweet is local to our aggregator crate. We can also implement summary on vector t in our aggregator crate because the trait summary is local to our aggregator crate. However, we can't implement external traits on external types. For example, we can't implement the display trait on the vector within our aggregator crate because display and vector are defined in the standard library and are not local. That makes sense. We can't modify external crates. That's really cool. That keeps things safe, right? This restriction is part of the property of programs called coherence, and more specifically, the Orphan Rule. So named because the parent type is not present. So the parent's not there, we can't operate on it, right? This rule ensures that other people's code can't break your code and vice versa. Without this rule, two crates could implement the same trait for the same type, and Rust wouldn't know which implementation to use. So very cool. That's that extra safety that Rust is giving us. I like that. Default implementations. Sometimes it's useful to have default behavior for some or all of the methods in the trait. instead of requiring implementations for all methods on every type. So instead of having each type have to implement it, we can create a default. Like, so if you don't implement it, it'll have a fallback, right? Then as we implement a trait on a particular type, we can keep or override each method's default behavior. So below, we can show how to specify a default string for summarize method of the summary trait instead of only defining the method signature as we did in listing 1012. So here, what it's saying we can do is, let me just comment this out, and I'm just going to say trait definition without a default implementation. That's what we have here. And then here we have one with a default. So summary, same thing, but we're going to actually define summarize here. So again, it's going to take the instance, which is what the reference to self is. It's going to return a string, but we're giving it an implementation here. Oop. String. And our default implementation is from read more. Cool. So now we have a default implementation. That's pretty cool. To use the default implementation to summarize instances of news article instead of defining a custom implementation, we specify an empty implementation block with implementation summary for news article. So let's try that. I know we've already implemented news article, so what I'll do is I'll comment this out. So I would say, I'm just going to put a comment here that says, this would override the default implementation of summarize. And here I'm just going to put so here we have an article, and I have to just put implementation block summary for a news article. So just an empty block. So we'll copy this. There you go, empty block. Now I'm gonna just go ahead and run this code. Let me move out of your way. Always in your way. And there you go, read more. So we just define it. And the reason we have to do this is we still have to say, hey, this thing should have a summarize function, right? It implements that. This way, if we are passing this thing as a generic, you could still call the summarize method on it, but it's going to just default to the default behavior. Whereas here, we actually implemented our own behavior, overriding that default. So really cool. I mean, there's so much stuff to this language that it's really powerful. And I'm sure we're going to figure out like what to use when, and as we start writing stuff, figure out what works best. But really cool to have this kind of functionality. Okay. Even though we're not defining the method directly, we provide a default implementation and specify a news article implements the summary trait. As a result, we can call summarize. So creating a default implementation for summarize doesn't require us to change anything about the implementation of summary on tweet. We can keep it. It's just going to override it. The reason is that the syntax for overriding a default implementation is the same as the syntax for defining it, right? Default implementation can call other methods in the same trait, even if those other methods don't have a default implementation. In this way, a trait can provide a lot of useful functionality and only require implementers to specify a small part of it. For example, we can define the summary trait to have a summarize author method, whose implementation is required, then define a summarize method that has a default implementation that calls summarize author method. So what does that mean? We're going to define a summarize author that is required. It's not going to have a default implementation. And therefore, because it's required, we can call it from our format. So let's do that. So we're going to have summary. We're going to have summarize author. It's going to take self, and we're not going to create a default implementation. So again, we're going to use that semicolon. And then in here, our default, it's going to say read more from, and then we're going to go ahead and call that required implementation self.summarize author. Now, this is pretty cool, and here's why. Look at right away what's happening. So we got some complaints. Missing summarize author and implementation. Missing summarize author and implementation. So Rust, again, we're getting this benefit of this compiler. Look at this. It's telling us right away, you haven't implemented this required thing. So that's really cool, and we're going to do it. So let's implement it. To use this version of summary, we only need to define summarize author when we implement trait on a type. So for news article, which we haven't implemented right here, we're going to implement the author one. So let's do that. So we're going to say summarize author. It's going to take this is the signature. And what we're going to do is we're just going to return format. Well, actually, we don't even need to format it. We can just return self.author, right? And then we can do the same thing here for our tweet, where they're using the username, but with the clever @ symbol here. So here we're just going to do format, and they have the @ right, like we would see in a Twitter handle. And what we're going to do is just format the author into here. Although it's actually username, right? Awesome. So now let's see what's up here. What is this saying? Oh, well, here I have to do that to return a string. This is saying you can't create a string from a literal string with string from. Oh, that's because I have to call format instead of string from. I'm going to do format. There we go. All right, so let's go ahead and run this. I'm just going to see, and it should still print out the same thing. Oh, one thing worth noting here, cannot move out of self-author, which is behind a shared reference. So we'll just want to just do this to create. We'll just do this to create another string from it. There we go. All right, so it probably was also acceptable to do this. No, not. Okay, so we'll do this. So let's run it and see if it still works. And there you go. Read more from Tom McGurl, and then thanks for joining the stream. That's our summary. Again, it's not using the author, but we can use it in our tweet. So let's do that. So in our tweet for summarize author, here we'll do, instead of username, we'll do self.summarize author. And if we run that again, we should see the @ in front of our name there. Yep, @Tom McGurl. Thanks for joining the stream. Thank you again for joining the stream. It's great stuff. Okay, this is fun. Very cool. I'm liking the traits, and now I'm starting to understand what some of those traits were that we talked about before. Remember, we talked about the copy trait. So, super fascinating. All right, traits as parameters. Now that you know how to define and implement traits, we can explore how to use traits to define functions that accept many different types. For example, in the listing below, we implemented the summary trait on the news article and tweet types. We can define a notify function that calls the summarize method on its item parameter, which is of some type that implements the summary trait. To do this, we can use the implementation trait syntax like this. So again, we're going to create a notify function that takes an item that implements summary and just calls the summary on it with some prefix in this case. So let's do that. So pub function, it's a public function called notify, takes an item, the item just has to implement summary, and here we're going to call println breaking news, and we'll just call item.summarize. And again, it's a reference, right? It's a reference to an item that implements summary. And so we're going to go back in a second and change that larger, because I think I already know how to do it. Rust. Let's go. All right, so let's try running it. Let's call notify. That'd be useful, right? So here, instead of doing this, I'm going to call try using, let me move over here, out of your way again. I'm always in your way. Come on, Tom. Try using our new notify function. And so I'm going to call notify, and I'm going to pass it an item. What item? I'm going to pass it article. And again, reference, right? What is this saying? Notify item. What does it want? Let's see. Expected one of period, comma, operator found, notify. That's because I didn't put a semicolon here. So we're gonna notify the article, and we'll also notify the tweet. And let's run it. And there you go. Breaking news. Read more from Tom McGraw. Breaking news. Tom McGraw, thanks for joining the stream. Thanks for joining the stream. You get sick of me saying that, right? Okay, so what does that mean? Really quick. I know they're gonna have us do it. We're gonna jump ahead. We're gonna just do it ourselves. We're gonna go back here. And now we know. And it kind of gave us a clue. It kind of told us already a little bit about it. But we're gonna go ahead and say that it should take a list, right? Instead of a T, of an implementation standard compare, what was it? Standard compare. Here, wait, let's get that hint back. We got a hint before we did this. Standard compare order or something. All right, I'm gonna cheat real quick and go back here. Oh, let's see. Let's try to figure it out. So we had type T. It gave us some complaint. Cannot be applied in type T. We took this away, and it said expected reference. Right. We got that. I think it was when I tried to compile it. Let's try that. So let's run cargo check on this. I'm just going to back up a little bit. Generics cargo check. I think we have to use it first. Oh, first we have to save it. Let's run that again. Here we go. Partial ord. That's what I want. All right, so I'm gonna steal that partial ord. Let's steal that. Let's see if we can get this thing to work. So it takes a T of implementation, implements standard P partial ord. All right. Expected parameter type T. That's because of this. You know what? Maybe we can even say, well, let's see if this, I don't know if this is how we're supposed to find it. I'm sure they're going to tell us in a second. But just so we can see if we can get it to work. Whoo, look at that. Let's see if it works. Let's see if it works. And I bet there's a way to simplify this. But let's see if this works. Largest. Oh, and so here it's saying it doesn't implement display because it doesn't know. It just knows that it implements this. Yep. But hey, we're almost there. I think we're going to find out pretty soon how to do this. So let's just put what we had here. And we'll jump back over to traits. We'll come back to this, but pretty cool. All right, so I'm just going to jump back over to traits. Okay, so let's continue. We tried to jump the gun. I know, I'm sorry, I apologize. Let's see. Trait bound syntax. The implementation trait syntax works for straightforward cases, but is actually syntactical sugar for a longer form, which is called trait bound. It looks like this. Okay, so this was the... So here, instead of the concrete type, we specified the implementation parameter, we specify IMPL keyword and the trait name. This parameter accepts any type that implements specified trait in the body of the notify. We can call any methods on item that come from the summary trait, such as summarize. We can call notify and pass in any instance of news article or tweet. Code that calls the function with any other type, such as string or 32-bit integer, won't compile because it doesn't implement summary. Okay, here's the other syntax. If I just waited, if I was just patient, I would have got to the exact thing I need to read. Here it is. The implementation trait syntax works for straightforward cases, but a syntactic sugar for longer form, which is called a trait bound. It looks like this. Notify T summary. Item at T. So let's change our notify function to look like that over here. So I'm going to say implementation trait syntax, and then we're going to say down here trait bound syntax, and it's going to be a little bit different, but basically do the same thing. And so function notify takes a T, which implements summary, and it's an item of type T. Pretty cool, pretty cool. So I'm just going to go ahead and change this real quick. So T is going to be T colon standard compare partial ord. And now we're going to go ahead and return type T here because we know that T we'll get that later. We'll get there. Okay, that's pretty cool. Longer form is equivalent to the example in the previous section, but it's more verbose. We place trait bounds with the declaration of the generic type parameter after colon inside angle brackets. The implementation trait syntax is convenient and makes for more concise code in simpler cases. Trait bound syntax can express more complexity in other cases. For example, we can have two parameters that implement summary using the implementation trait. Syntax looks like this. So we have function notify, item 1, implement summary, item 2, implement summary. If we wanted the function to allow, let me put that here so we have a nice notify, item 1. I'll just copy, whatever. Pretty cool. If we wanted this function to allow item 1 and item 2 to have different types using the implementation trait, we would appropriately, as long as both types implement summary. If we wanted to force both parameters to have the same type, that's only possible to express using trait bound like this. So if we wanted to make sure they were the same type, we would use trait bound. So I'm putting here two args that can have different types. And then we're going to just copy this. And we're going to say Rustafarian. Oh, I like it. It's like the new Rustations. That'd be our band name. And we'd be Rustafarians. Two args that have to have the same type. The same type. So here we're going to do notify is going to be, this is the trait bound syntax summary, and item 1 is going to be T, and item 2 is going to be T. The generic type T is specified as the type of item 1 and item 2 parameter constrains the function such that the concrete type of the value passed as an argument for item 1 and 2 must be the same. Similar to what we saw when we had T and we need to add the U to allow for different types in our struct. Specifying multiple trait bounds with the plus syntax, we can also specify more than one trait bound. Say we want to notify to use display formatting on item as well as the summarize method. What does it sound like? Come on, this is exactly what we're about to do. They're leading us up. They're just leading us up to do this, right? Come on, this is crazy. Look, it's even when I hover, look. Come on, we're gonna get there, I'm excited. So we can use the plus syntax to say it must have summary and display. And here is the example of that. I'm gonna copy this because it's super cool. And we'll just say, using the plus syntax to show it must have two traits. Not implement, this isn't function, this isn't classes, this isn't object-oriented, Rustafarian. Nice, Doze, welcome Doze. It's always good having Doze here in the chat. We got the usual suspects. We got Clam Watson showing up. Love it. Love to see it. All right, so here's this version. That's pretty cool. The plus syntax is also valid with some trait bounds on generic types. Oh, cool. So here we have notify T, summary display. So that's probably what we're going to do with our largest function. I bet. Are they going to get us to do it? Oh, I'm going to sneak ahead. No. Yeah, look. Go back up, sorry. Too soon. All right, cleaner trait bounds with where clauses. Ooh, so there's so many ways to do things. Using too many trait bounds has its downsides. Each generic has its own trait bounds. So functions with multiple generic type parameters can contain lots of trait bound information between the function's name and its parameter list, making the function's signature hard to read, and it breaks up on multiple lines and blah, blah, blah. For this reason, Rust has an alternate syntax for specifying trait bounds inside a where clause after the function signature. So instead of writing this, function without where clause, we can write this. So let me put here some function, well, we can just call this without where clause, some function with where clause. Okay, so let's see what this is doing. So it's parameterized over T and U, and then in the body at the right before, so like right after the return type, actually, right before the start of the block. I'm just going to turn this so it doesn't complain. We're saying where T implements, or T has the trait. I'm going to keep saying implement. What am I doing? Doe's in the chat. Let's go. I don't know, man. Can't answer that one. It's because you're not typing. You have those hands free, so you're doing silly stuff. All right, where T has the traits display and clone, and U has the traits clone and debug. Come on. This is some cool stuff. The function signature is less cluttered. The function name, parameterless, and return type are close together, similar to a function without lots of trait bounds. Okay. We're doing good, chat. We're at 10:30. I think we'll definitely at least get through this traits portion. We might have to carry the other part over to next week, but whatever. Chapter 10, we knew. We were here. We're like, yo, chapter 10 is going to be nuts. I was running into people on the internet. They were saying, oh, chapter 10, it's going to be nuts. Just around the virtual water cooler, people were just like, I've heard this chapter 10 is quite the character. They were talking about some guy named Fuke, and they were also talking about chapter 10 by the water cooler. Pretty cool. All right. Return types that implement traits. We can also use the implement trait syntax to return position in the return position to return a value of some type that implements a trait as shown here. So here we're saying returns summarizable, returns something that is implementing the summary trait. So I'm going to just define that. Let me just go ahead and comment this out so I can get this stuff to run. And let's create this because this is kind of cool. And we're going to be doing it in a second. So function returns summarizable, and it's going to return a type summary, something that implements summary. And what implements summary? Well, let's create a tweet, and let's just copy our tweet here. We'll change it a little bit. Don't worry. And so we'll change the username. We'll keep the username as Tom McGurl. We'll change this to, we made it to chapter 10 crustaceans. All right. And so this works because this implements summary. If we change this to something that didn't, for example, struct point let's use our generics. If we did this, this would complain because we're not returning something that implements summary. So pretty cool. That's really, really powerful stuff. So then you can trust that if you call return summarizable, you'll know that whatever gets returned from this function, you can call summarize on with no problems. And more important, Rust knows, and it'll successfully compile. What a tease chapter 10 is. Yeah, chapter 10, we thought it was gonna be this huge thing. It's like getting real technical. It's like, that's why I wore my glasses today. I was like, we're gonna get real technical. We're gonna go in it. No examples. No, I mean, lots of examples, but yeah, not many. Last chapter was really fun. I'm actually enjoying this though. I think it's fun, but it is definitely not like the big chapter 10 that we were. I was expecting a video, maybe some GIFs. I was gonna, like, if it got crazy, maybe just have like some, on stream party. Who knows? All right. By using implement summary for the return type, we specify that the return summarizable function returns some type that implements the summary trait without naming the concrete type. We don't care as long as it returns as long as it has the summary trait or implements the summary trait. In this case, returns summarizable returns a tweet, but the code calling the function doesn't know that. All it knows is that whatever it gets back, it can call summary on, no problemo. The ability to return a type that is only specified by the trait it implements is especially useful in the context of closures and iterators, which we'll cover in chapter 13. Closures and iterators create types that only the compiler knows or types that are very long to specify. The implementation trait syntax lets you concisely specify the function return type. Specify that the function returns some type that implements the iterator trait without needing to write out a very long type. However, you can only use the implementation trait if you're returning a single type. For example, this code that returns a news article or a tweet with the return type specified as in summary wouldn't work. Interesting. So this wouldn't work. It can only return one type that implements summary. Returning either news article or tweet is not allowed due to the restrictions around how the implementation trait syntax is implemented in the compiler. We'll cover how to write a function with this behavior in using trait objects that allow for values of different types in chapter 17. That's very specific. We're going to get there. Maybe. Who knows? Fixing the largest function with trait bounds. Here we go. This is our function, right? Let's go ahead and pop over to largest here. Now that we know how to specify the behavior we want to use using the generic type parameter bounds, let's return to listing 10.5 where we define the largest function that uses the generic type parameter. Last time we tried to run that code, we received this error. Yes. In the body of largest, we want to compare two values of some type t using the greater than syntax, but the operator is defined as a default method on the standard library trait standard compare partial order. We need to specify partial order in the trait bounds for t so the largest function can work on slices of any type that we can compare. We don't need to bring partial order into scope because it's in the prelude. Again, the prelude is what Rust already brings in for you. It's commonly used things. Greater than, less than, very common coding, right? Change the signature of largest so it looks like this. So let's see if we were close. Kind of. We didn't need to pull this in like this, so that was one mistake. What else? We didn't use T here. Otherwise, we got that part right. We have list, and let's see what it says here. Expected type parameter T. Oh, so here it says, this time when we compile the code, we get a different set of errors, and it's because they had list. The key line in this error is cannot move out of scope T, a non-copy slice. With our non-generic versions of the largest function, we are only trying to find the largest of 32-bit integers or characters. As discussed in stack-only data copy section chapter 4, types like 32-bit integer and character have a known size can be stored in the stack. So if you have the known size, you can store in the stack. So they implement the copy trait. When we made the largest function generic, it became possible for the list parameter to have types in it that don't implement the copy trait. Consequently, we wouldn't be able to move the value out of list 0 and into the largest variable, resulting in this error. To call this code with only those types that implement the copy trait, we can add the copy trait. So let's go ahead and do that. So we need to change this. So here we're going to use our plus. Pretty cool. All right, so we're adding the copy trait. We can add the copy trait to the bounds of t. Below we have the complete code of the generic largest function that will compile as long as the types of the values in the slice that we pass into the function implement partial order and copy. And so here we have largest item. What is it? Oh, well, first off, I have to get a reference to item. All right, so here we see that it's now working. We can get rid of this. And again, they implement the copy trait, so we're no longer getting a reference. You can see in the function signature here, we're getting the actual value. So we can get rid of our destructure or dereferencing there. And if we just see if this works now, let me move out of your way. We're gonna run it. There we go. Everything still works. That's awesome. If we don't want to restrict the largest function to types that implement copy trait, we could specify that t has the trait bound clone instead of copy. Then we can clone each value in the slice we want the largest function to have ownership. Using the clone function means we're potentially making more heap allocations in the case of types that own heap data like a regular string, like not a pre-allocated string, right? And heap allocations can be slow if we're working with large amounts of data. So because we know we're only working with 32-bit integers and characters and they're allocated on the stack, it's safer to just say we want to use copy. Another way we can implement largest is for the function to return a reference to a t value in the slice. So instead of just the direct t value here, we can return a reference. If we change the return type to reference of t instead of t, thereby changing the body of the function to return a reference, we wouldn't need the clone or copy trait bound and we could avoid heap allocations. Try implementing these alternate solutions on your own. So we'll do it. Let's do that. Let's do get rid of this. Reference to item. And what is it saying here? Let's see what largest says. Expected t and found parameter t, so we're just going to return a reference there. There we go. And let's see now down here. Let's try to run our code. And we have a problem. Can I compare a reference character to a regular character? Expected reference of t, found parameter t. So what if we did there we go. Let's see. So now what we're doing, instead of having a reference, we actually have the value, right? And so we can compare against a real value. And now it's saying no implementation for, because we have a reference. So again, because we're returning a reference, we have to go back here and just make sure we grab the actual value in both of these cases here. So let's see if that works. No. Returns a reference data owned by the current function. Cannot move item, which is behind a shared reference. That's probably because I have to do this. And then here we do the same thing we had before, where we grab that. Largest is now going to be a reference. And so we want to compare largest. Item is a oh, well, now we're back to where we were. But at least we have the reference to this. Oh, wait, you know what? Expected a reference of t, found a regular t. So we want to make it a reference of t. Oh, I'm very confused now. List 0. Oh. Wait, hold on. Yeah. What's happening? Pointers. Just keep adding asterisks. Let's see. What does it say here? Let's see if they have any tips. Another way is for the function to return a reference to a t value in the slice. If we change the return type to a reference of t instead of t, changing the body of the function to return a reference, we wouldn't need to clone or copy trait bounds, as we could avoid heap allocations. So let's see. We're returning a reference of t. Here, this is definitely a reference of t. In our for loop, we want to loop over the list. All right, what's happening here? Oh, there we go. It was right. I hadn't saved it. I'm silly. There we go. What do we do? So we have a reference. We're returning a reference of t. We grab a reference to that list, pop it in largest, right? That number, largest, is a reference. We do the comparison. This is reference comparison, reference to reference, right? So it works. It all works. And we return a reference, and then down here, we just get the value at that reference. Beautiful. And look, Rust told us all along the way what was happening. It's amazing. All right. Woo. Chapter 10. It's getting crazy. Not really, though, right? It's not too bad. A lot of reading, but again, this is this type of stuff where we're doing the reading. Usually I jump in and just start writing code, but this is going to give me the foundation so that when I go to learn Rust, which is a very different language than something I'm used to, I'm not going to go bang my head against the wall and not understand what all these symbols mean. So I think it's a pretty good way to learn this stuff. Using trait bounds to conditionally implement functions. Ooh, interesting. By using a trait bound with an implementation block that uses generic type parameters, we can implement methods conditionally for types that implement the specified traits. For example, the type pair of type t in the listing below always implements the new function, but pair t only implements the command display method if its inner type t implements partial order, trait that enables comparison, and the display trait that enables printing. So conditionally including, that's pretty nice. So let's see what's going on here. So first, I'm going to go ahead and import the display. And again, display is that is when we do the, when we are using format, we use the curlies. We're actually passing it something that implements display. So we pull that in. I'm going to create function pair. Oh, I'm doing this in the wrong file. First of all, what am I doing? Go over to traits. Standard format display. Pull that in. Down here, I'll just do it above our main function here. I'm going to go ahead and do struct pair, which is parameterized over t, where x is of type t and y is of type t. We're going to create an implementation block parameterized over t using the pair t. And we're going to create a new function that takes an x of type t, a y of type t, and returns an instance of pair. And it's going to just return an instance of pair. Cool. And here's the conditional implementation. The conditional implementation is going to be over a type t that implements the display and the partial order traits. So it's going to be for only t's that implement the display and partial order traits. And we're going to have, oops, sorry. Yeah, that looks right. Oh, I forgot the L. I'm like, why does it not look right? Okay, and then the function is compare display. And we're going to do something that's going to require those functions, those traits be implemented because we're going to use some functions that we expect to see. And so if self.x is greater than or equal to self.y, we're going to print, let's just copy this. I don't want to type all that printing. Largest number is x and self.x. So the reason we need to implement compare, or in this case partial order, which is a type of compare, the reason we need to implement this is because our function is leveraging it with this greater than or equal comparison. The reason we need to implement display is because we're leveraging it using this. Now, if we wanted to use this, for example, we would say that we need to we need to implement debug as well, because that's the debug trait being used. But we're not using that, we're using display. So that's how that's going to work. We can also conditionally implement a trait for any type that implements another trait. Implementations of a trait or any type that satisfy the trait bounds are called blanket implementations and are extensively used in the Rust standard library. For example, the standard library implements the toString trait on any type that implements display trait. The implementation block in the standard library looks similar to this code. So implement anything that has display, toString for T. Pretty cool. Because the standard library has the blanket implementation, we can call the toString method defined by the toString trait on any type that implements the display trait. For example, we can turn integers into their corresponding string values like this because integers implement display. And that's why we're able to print integers too, right? So pretty cool. Blanket implementations appear in the documentation for the trait in the implementers section. Traits and trait bounds let us write code that uses generic type parameters to reduce duplication, but also specify to the compiler that we want the generic type to have a particular behavior. The compiler can then use the trait bound information to check that all the concrete types used with our code provide the correct behavior. So we make sure that when we're using these types, they have this behavior. Then we can use that behavior within our functions and we have that safety, right? In dynamically typed language, we would get an error at runtime if we called a method on a type where we didn't define that method. And that's happened. If you've used JavaScript, I know that's happened because it happens to everybody. Cannot call blank of undefined, right? How many times have you had a function where either in runtime, hopefully not in runtime, but yeah, it happens obviously. You get cannot call toString of undefined or cannot call blank of undefined or toJSON of undefined. And that's because the undefined doesn't implement a toString function or undefined doesn't implement whatever function you're calling on it. And that's a case in a dynamically typed language where you get a value you didn't expect. You didn't expect undefined. What if you could say, hey, this function will only operate on values that implement this method, and you can have the compiler check for that. So pretty cool. But Rust moves these errors to compile time, so we're forced to fix the problem before our code is able to run, right? Additionally, we don't have to write code that checks for behavior at runtime because we've already checked at compile time. Doing so improves the performance without having to give up the flexibility of generics. So we don't have to do those checks like, if it's undefined, do this. Obviously, there's code like that, like if we're dealing with option or result, but in this case, we don't have to do those checks. Another kind of generic that we've already been using is called lifetimes. Rather than ensuring that a type has the type of behavior we want, lifetime ensures that references are valid as long as we need them to be. Let's look at how lifetimes do that. So I think the lifetimes is a pretty lengthy section. Indeed it is. So we are at, we're at 10:50. So we're going to cover lifetimes next week, and then we'll go from lifetimes into automated tests, which will be pretty fun. We'll write some automated tests. So that's going to be it for today. Lifetimes to follow. We covered generic types. It was a lot. It was a heavy day. Chapter 10, we knew it was coming. It wasn't as exciting maybe, but it was pretty heavy. We did some fun stuff. We write a lot of code samples. All the code we wrote here today will be posted on GitHub. After this, I'll be pushing it up. Again, if you missed any part of the stream, you joined late, you want to catch up, everything is going to go up there on YouTube. The video will be posted tomorrow up here on YouTube. If you missed any of the other chapters, go back, check them out, watch them on whatever speed you want to watch them on. Maybe you want to watch them on 1.7 speed, 2x speed, whatever. Maybe watch them while you're making your coffee. You're like, let me throw on some Tom in the background. You know, I'm getting ready in the morning. Maybe you're on your like bicycle, your stationary bike. You all got one of those, right? You're on your stationary bike and you're like, I could be watching some Rust videos, right? Or not. I mean, you probably, don't put this on like the family room, right? Nobody wants to see this. But the video will be posted here. It'll be part 10, covering chapter 10. Wow. And then next week, we will cover traits. Again, if you want updates on when I'm going live, give me a follow there on Twitter. It would be greatly appreciated. If you're watching on YouTube and enjoying it, you hit that subscribe button. Classic, hit the subscribe like button, but you got to do it. Come on, you got to do it. You're making videos, you got to do it. Hit the subscribe button, hit the like button, and you will get notifications when I go when I upload new videos, so you'll be notified when this video goes up and any other videos. If you joined live on the stream, thank you so much. It was awesome having you. It's always great seeing returning faces or returning usernames. Not seeing your face. Not yet. Maybe I'll write a Rust program where I can. No, not yet. But yeah, and then also check out the GitHub where we'll have the code for this. So thanks again for joining the stream. It's been a fun time. Again, this is Tom McGurl's Twitch channel. So come back. Happy to have you. And again, the YouTube channel, Twitter's up there. Thank you. This was a fun time. I've been really enjoying it. And like I said in the beginning, I may add some more days, may add some more one-off content for YouTube. I'm putting that up there. Jeff Erroneous, thank you for the follow. Loves to see it. Awesome. Happy to have you. Really appreciate the follow, Jeff Erroneous. That's awesome. And I will see all of you, hopefully, next Tuesday. Everyone have a good night and enjoy our journey into being Rustaceans. I think we're like basically almost Rustaceans now. Just catching the end of the stream. No problem, Jeff Erroneous. We'll be here next week, 9 to 11 p.m. And if you missed it, I put everything up on YouTube. So just check it out there, right up top. This will be up tomorrow morning. Appreciate the follow. Appreciate everyone in the chat. Thank you, and I'll catch you all next week. Good night.